Okay, now so we're looking inside the machine for a closer view. So basically, I'll first just show generally how kind of I control the machine when I'm going to set it up and so on. So I have, as I said, I have a PC that runs a Mach 3 on it. But what I do is I have a tablet and then I remote into that machine. So basically, when I want to put in a workpiece, what I have to do is I have to zero this tool, it's called, bring it to like 000 on a ZY axis, and then I run a cutting profile from there. So if you don't know what kind of I'm talking about there, you probably haven't been involved in the CNC machine before, but so I'd maybe come back to that at a further time. But effectively anyway, I can move the machine around using these keypads, so I can move this guy around here, literally back and forth, etc. You know, so it's very, very handy in that way. So we'll go through the inside first. So basically a workpiece is actually clamped down here. I'll just move this out of the way. A workpiece is clamped down using these clamps, and basically this is just Allen head bolts. And then I have this guy, these wooden kind of slates, and effectively they've all been machined down, so this is perfectly level. This is absolutely level, right? Because you know, it's vital that you know that literally Z0 over here is exactly the same as Z0 here, right? So you can put a workpiece down and it's perfectly flat. Okay, so I'll go through the different axes and the design, etc. So this is the water-cooled spindle, and we have water in and water out. And then what I have here is this is a shielded cable. It's basically there just to provide power purely to this spindle. I changed the tool here to some form of a collet, you know, which can be taken off. So what you'll see up here is the stepper motor. And basically right in behind it, this is a ball screw here, and effectively then there's some form of a coupling. Now this was the most expensive part of the actual build. All of the timber literally only came to about 150 euros, so that's quite a small price to pay. It's not a lot of money at all. But what provides a lot of rigidity to this machine is these SBR rails, they're called. And basically what you have is some form of it's effectively like it's a linear, half-round linear bearing which clamps onto this rail here, and then you can just slide it up and down. So effectively I had to go off and buy something that was a 1.5 meters by 1.5 meters for both X and the Y axis that you see here, and basically then buy the ball screws, which would be in the same category. And then effectively it's very difficult to see it, but effectively in behind the axis you have this kind of a nut which clamps on to the actual axis, so they can move around. So as basically the steppers turn and then the ball screws turn, the axes are forced to move out. So that's an example of that there. There's a nut in behind, as you can see, rotation here. So effectively what you can see is that I have like a build where I have this rail piece here, and then all I did was I put on this kind of an MDF section, and I had a very, very simple design in mind. Keep it as simple as you possibly can. I made each of the axes out of MDF, and then what I did, which is the cleverest thing to do I think just in general, because in order to go off and build something like this you really have to do your homework. I didn't build out of aluminium extrusions. What I did was I built out of MDF bolted onto steel box beams. So there's the strength of steel literally behind this, and not aluminium. Aluminium extrusions, which can actually look quite well, but they lack the strength, you know, over time. You know, because you can have a certain amount of distortion and creep the more that you run a machine like this. So the frame itself is just MDF and it's pine beams, but the strain is put on these axes here, and with the steel behind it, along with the rails themselves, you get real rigidity as it's kind of powering along. So what you can see here is these cable drag trains. So the cables, the actual power to the motors themselves, along with the power to the VSD, that runs through the actual the drag train here. Okay, and what I decided to do with regards to the coolant system literally just hangs. It hangs from here, and this is kind of like a very durable PVC. I was afraid of running the water through the drag trains, so effectively what I have is the water pipes just hanging and then going up to the top. You can't really see it there, it's just barely, but you can see them. They kind of there. You can see it kind of slightly move in the background. Effectively, it's what I felt was the best thing to do, and if I ever wanted to add a suction system onto it, I'd probably just do the same thing. You can't exactly run the suction system through the cable drag train. Okay, so the cost of the rails and the ball screws, etc., and these couplings here and the motors, that's something that came to about 650 euros. It's something that you have to go off and you have to try and get the best price that you can, but effectively you're going to pay a certain amount of money and then you're going to pay for postage. Unfortunately, these things are heavy and they're very long and awkward, and when you go off and you're going to buy 3 stepper motors as well, you're going to literally pay a certain amount out. And what I probably didn't actually include on that, was the stepper motors include the cost of the actual drives. So you're going to pay a certain amount. You can do what you can do, but still 650 euros for 4 steppers of very decent power and quality, along with 4 stepper drives, along with then 1.5 meters long, and you have literally 2 sets, so, and then along with a Z-axis then, that for 650 euros is doing extremely well. Okay, and the final thing what I wanted to say was that sometimes you see in people's designs the x-axis is all the way up here. Now that's generally, I don't understand that. I really don't. I fundamentally, the thickest piece of material that I can literally machine is 80 millimeters, and that's completely fine, because most of the time in a machine like this, what this was built for was cutting basically boards that were generally going to be no thicker than 20 to 25 millimeters in thickness. So if you keep the x-axis down literally as near to the y-axis as possible, you'll get the most rigid design possible, and that's pretty much something that I just wanted to clarify then at the very end.